Hi, I'm Grant and welcome to the second study session in the AGK series. Today we're going to be answering some questions on the question bank all about electrics. We've spent the last few classes looking at electrics, so now is a good time to pause, answer some questions and reflect on what we've learnt, maybe find some weak spots and find out what we need to study a bit more of for the exam. Hello and welcome to this study session for the electrics portion of AGK. We've finished everything to do with DC and AC electrics, and it's quite a big topic, so I thought it was worth doing a little study session before moving on to all the other systems that are covered in AGK. So business as usual for the last few study sessions that I've done. I've gone through, I've selected all the questions and then essentially hand-picked some ones that I saw so that all the questions aren't on the same topics, so there's quite a nice spread of topics. So there's things like DC, AC, motors, generators, all the way down to the basics of like what resistance is and all that kind of stuff. So yeah, it should get a good variety. I've not actually answered the questions, I've just looked at the titles and scanned through. And we're going to be using the Airhead ATPL question bank. As ever, link below in the description if you want a little discount, and we'll go through some of the features and highlights of it as we start. Got my little notes app ready to go, should we need anything on the side there, but for now I'll just minimize it and let's get started. AGK Electrics study session. Okay, starting off, question 1. Which system has an integrated combination of an AC starter motor and a generator? So it's not going to be an APU because that's just a generator. It would start off of the battery. It's not going to be the RAT, the ram air turbine. That's the little propeller that drops out of the bottom of the aircraft to power an emergency generator. A starter generator makes sense because it's a starter motor and a generator, so starter motor and generator, and a 3-phase AC generator doesn't necessarily have an AC starter motor, so I'm going to go for starter generator. A DC electric motor slows down due to an increased load. As in, yeah, cool. The armature current will what and the torque will what. So let's just bring this up. So in order to not confuse ourselves, option 1, option 2, the armature current will something and the torque will something. So if there's an increased load and it's slowing down, that means the torque on the armature has gone up and it's got to push more. So that's gone up. And that means that it slows down due to an increased load because it's got too much torque for what it needs. The torque goes up. Or does that mean that the torque goes up to power through it? So it's slowing down. I think if the torque goes up, the current must go up as well. So let's go increase, increase. Correct. Let's look at the options. That's a good one. As the load on the motor increases, it requires more torque to maintain its speed. Yes. To produce the additional torque, the motor needs to draw more current from the power source, therefore the armature current increases to provide the necessary torque to overcome the increased load. Yeah, so if there's more load, you need more torque. To get more torque, you need more current. That's essentially what that is saying. Cool. Next question. A constant speed drive CSD that has been disconnected in flight can be reset in flight using the reset mechanism, can only be reset on the ground after engine shutdown, automatically resets on engine shutdown, automatically resets providing blah 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 blah. So it's not going to automatically reset because you don't know what's caused the problem. Engineers would have to go in there and find out. And again, you don't want to do it well, it'd be very hard to do it in the air because again, you can't check it. Engineers can't go up and check what the problem is. If you've disconnected it, it's generally because of a problem. It's within the internal workings of the engine and the gearbox and stuff, so you can't exactly just reset it without having a check on it first. So option 2, which is correct. Question 4 then, what happens if one cell in an aircraft battery experiences thermal runaway and catches fire? So this is basically going to ruin the battery, because if one cell's on fire, it's not going to be good. But anyway, aircraft batteries are constructed in such a way that they regenerate themselves after a thermal runaway. What? So any fire will be limited to small flames and difficult to detect. They regenerate themselves, do they? Not true. The fire will be isolated in the cell in question and not spread further, although it might cause minor damage to neighbouring cells. I mean, I think that's kind of what you hope to happen. If a fire is isolated, you don't want it spreading further. The fire will spread through the battery until the pilot turns off the battery switch, at which point the fire will stop burning. No. The fire will spread to neighbouring cells and spread through the battery, destroying it. So I think that's ideally what you would like to happen, but I don't think that does actually happen, because you get thermal runaway essentially. You get one cell heating up the next one, heating up the next one, and destroying the battery. There we go, correct. Question 5 then, which of the following power supplies can be used with a load that can withstand non-constant AC power? Which of the following power supplies can be used with a load that can withstand? So non-constant AC power is going to be an inconsistent frequency. So power supply, a wind turbine is going to give you a pretty consistent frequency. They're designed to do that. Battery doesn't have anything to do with frequency. Solar panel, I'm not sure. I think solar panels do DC power. So I'm going to go for frequency wild, because that means that the frequency is all over the place, which means non-constant AC power, which is correct. I'll look at the explanation for that one. In a frequency wild generator or electrical system, there is no attempt made to control the frequency. Yes. This approach simplifies mechanical complexities of the engine-powered electrical generators that are now able to allow the frequency to vary with engine speed. So this is like if you didn't have a constant speed drive, you get a variable frequency. So let's have a look. Batteries produce DC, yeah. Wind turbines, they're made to run at a constant frequency, yeah. They've basically got a constant speed drive in them. And solar panels produce DC, as I guessed correctly. There you go. 6. The purpose of bonding the metallic parts of an aircraft is to, so this is those little strips of tape that you connect all the components together with. And that basically will, if there's different levels of charge on different points, and you didn't, say the nose had 10 volts of charge of static on it, and the tail had 6 volts of static, you get this sort of current flowing from the high to the low. So you don't really want that. You want no voltage difference between the different components, and you achieve that through these little strips that you bond together. So what does that even mean? Number 1, prevent electrolytic, I don't even know what that is, corrosion between mating surfaces of similar metals. If I don't really know what it is, it's probably a good sign that it's not been in the course. So ensure zero voltage difference between the aircraft components. Yes, that's what I was just talking about. That's 2. 3, isolate all components electrically. Jesus, I don't even know how to speak. So that's no, we're not isolating them. We're providing them, we're making sure that they're all sort of one. And 4, provide a single earth for electrical devices. So I'm going to say 2 and 4. 2 and 4, which is correct. Comments? Pathetic explanation. All right, God, somebody's not happy. Oh, I mean, pathetic's a bit strong. It's not the best, but yeah, Poor explanations, wrong answers, contrary. So people are not happy with ATPL GS. This is sort of the provider of the questions. So yeah, that's why you come and get this one, this Airhead ATPL question bank, because it's not just questions from that. You'd be a bit hard done by if you'd only signed up for ATPL GS. Whereas in this question bank, you get a few more options. Question 7, the input and output of a static inverter. So TRU, transformer rectifier unit, or a rectifier does the AC to DC, and a static does DC to AC. So input is DC, output AC. So DC input, yes. AC output, yes. Which is correct. An advantage of nickel cadmium compared with lead acid batteries is that they are more lightweight and less corrosive, but they produce less voltage. They also don't sort of fade away during discharge, whereas a lead acid battery starts to fade away. I'm not sure if I mentioned that actually, but we'll go for that answer. And it's right, and I'll look at the explanation to explain it in a bit more. So basically you've got the internal resistance of the components in the battery, and with a lead acid battery, this internal resistance increases at lower temperatures. So as it discharges and it's cooling down, it's not as reactive. This internal resistance goes up, which means that the voltage output goes down. And then with NiCad, it's kind of the opposite way around. So quite tricky. I recommend with these battery things to try and just remember the facts. Just do question bank on this sort of stuff because it is tricky. Which of the following statements is correct about an electrical fuse? The fuse must be as close as possible to the source to protect against short circuits. Yeah, I suppose you don't want all the components burning if you think about it like a component over here, and you've got the fuse here. I don't even know what the symbol for fuse is. Let's just give it an F. And you've got a big battery here. There's no point in having the fuse after the component because the component's going to blow before the fuse does. That's an absolutely terrible drawing, but it works. So the fuse must be as close as possible to the source to protect against short circuits. Yes. The fuse provides protection against voltage exceedances. It's more current exceedances that fuses are rated to. Upon reaching its normal amperage, the fuse instantly melts. No, it would be above nominal. Sorry, not normal. The fuse instantly melts. It wouldn't instantly melt, and it would be above. The rating of fuse is the amperage at which the fuse will instantly melt. No, so it'll probably allow brief exceedances, but anything sustained will cause it to melt. Yes. Oh, that's just a diagram of a fuse. Yeah, cool. Halfway then, in a three-phase AC generator, as the generator RPM increases, the output frequency, three-phase generator RPM increases the output frequency. So if you spin it faster, that means that the magnet is going to pass through the electrical fields more. If you think about the sort of the pairs, the three sets of stator magnets, if you spin this faster, you're going to get a high interaction here and then low. You're going to get a high interaction here, then low, and a high interaction here, then low, more often. So the frequency is going to go up. Simple as that. Yeah, if you spin it faster, you get a higher output frequency. One of the risks associated with the use of lithium-ion batteries in flight is So the big one here is thermal runaway. That's when I hear lithium-ion batteries, I usually just think thermal runaway is usually because we do a lot of training, especially cabin crew, in how to fight fires, especially lithium-ion fires, battery fires, things like laptops and phones going on fire because they run away and can stay on fire for ages. An excessive increase in temperature due to the evaporation of the electrolyte? No. One of the risks when the batteries discharge excessively? What? That's a rubbish answer. Overheating during charging, which could lead to self-ignition if not properly monitored. That's thermal runaway. Shorting the terminals, causing a high current flow, rapid heating, and risk of explosion. So it's during charging. Yes, there we go. The capacity of a battery is so this is amp hours, how many amps it can stay in for how many hours. 10 amps for 1 hour if it's a 10 amp hour battery, or 5 amps for 2 hours, any combination that makes 10, or whatever the battery is rated to. So no load voltage of the battery multiplied by its, no. Number of cycles a battery can withstand, no. Amount of ampere hours that a fully charged battery can supply, yes. Intensity withstood by the battery during charging, no. Yes. Explanation, yeah, exactly what I said. Ohm's law stated that in an electrical circuit, the voltage passing through a resistor between 2 points is proportional to the current. The current passing through is proportional. Right, okay, so Ohm's law is V equals IR. So let's just write that down. V equals IR. So this is going to be a bit of sort of manipulating this equation to figure out what the actual answer is. So the voltage passing through a resistor between 2 points is proportional to the current. So if the current goes up, the voltage would go up. Okay, let's try the other one. Try them all. So the current passing, so let's rearrange for the current. I equals V over R. And apologies if you can hear any background noise. There's some work going on outside that seems to be surprisingly loud. So yeah, just bear with me if you can hear anything. But basically the current passing through a resistor between 2 points is proportional to the resistance between those 2 points. The current passing through a resistor between 2 points is inversely proportional to the resistance. The voltage passing through a resistor between 2 points is inversely proportional to the resistance between those 2 points. So basically, let's think about it in terms of if we have more resistance, we have less current. You know, if there's, I'm going to bring it all the way back to like water. If there's more resistance stopping the water flowing, then the current would go down. So the current and the resistance are inversely proportional. The current is inversely proportional to the resistance. Current passing through a resistor between 2 points is inversely proportional to the resistance. That makes sense to me. The voltage passing through a resistor between 2 points is inversely proportional to the resistance in those 2 points. No, the current passing through a resistor between 2 points is proportional to the resistance. No, if there's more resistance, there's less current. So I'm going to go for this one here. And I think that's it. Yes. Okay, so maybe manipulating the equation isn't the best thing. If you can think like that, then good. Current passing through is inversely proportional to the resistance. Yeah, because the resistance is getting, you know, the voltage is divided by the resistance. Yeah. Sometimes you just get stuck on them and you got to think about other ways. I thought just writing the equation would help, but had to actually think about it a bit more. What directly controls the power required for field excitation of the main rotor in modern constant frequency alternators? Jesus, right, that just sounds complicated, doesn't it? Okay, so what directly controls the power required for field excitation? So field excitation is going to be like an electromagnet in the main rotor. Electromagnet in the main rotor, yeah, in modern constant frequency alternates. So the alternator doesn't control the alternator itself. An excitation alternator with a permanent magnet generator, the voltage regulator, or a battery. Oh, God. Right. What is it even asking here? What directly controls the power required for field excitation? So what is controlling the power to the electromagnet in a constant frequency alternator? So a constant frequency generator. An excitation alternator with permanent magnet generator, an alternator, a battery. Would the battery do this? Don't think so. An excitation alternator with a permanent magnet generator. Go for that one. Wrong. Okay. Had to get one wrong, obviously, so that you could show. I could show the explanation. It was all going so well. Right. So refer to the figure. The purpose of the voltage regulator is to control the output voltage of the generator at varying loads and speeds. For instance, if the electrical load of an AC generator providing a constant output voltage increases, the voltage regulator will increase the excitation current of the field coil, thus increasing the output of the generator and keeping the voltage constant for the increased load. Shunt wound DC generator. That was just quite confusing to me, actually, the way it was worded there. Power equals VI. The regulator directly controls the excitation. A video. There you go. So yeah, I need to look up alternator stuff would be my study point from this session so far. Question 15. For a brushless three-phase AC generator, how is the output voltage controlled? For a brushless three-phase AC generator, how is the output voltage controlled? So it's a brushless motor. We can control the output voltage by adjusting the torque of the drive shaft of the generator. No. RPM of the drive shaft of the generator. Current through the bridge circuit of diodes. Resistance of the field windings. Resistance would control the current flow. So if you increase the resistance, obviously the current will go down, not necessarily the voltage. So let's not go for that. Although they're all related, aren't they? But okay, so by adjusting the torque drive of the shaft generator, I don't think that makes any sense because you're just turning it with more force. The rotor. The RPM would do the frequency. We just had a question on that. Current through the bridge circuit of diodes. I'm not really sure what that even means. The bridge circuit of diodes or resistance of the... I think resistance of the field windings has to be it. Current through the bridge circuit of diodes. What the hell is this even talking about? I'm not sure about that question. Let's just call that a dud. 2 wrong in a row, that's not good. Anyway, on an aircraft with 2 main generators, if one generator fails, the bus bar is isolated completely. No, so let's get a quick diagram for this. This should help. So, aircraft will have 2 bus bars for AC systems. Just call them AC1 and AC2. Generally, they're powered by generator 1, AC generators 1, and generator 2. If this is to fail, you basically have a connection here, which is called a bus tie breaker, that will automatically link up so that AC bus 1 is powered from generator 2 as well as AC bus 2. So you get sort of a connection made between the 2 bus bars in the case that one of the generators fails. So the bus bar is isolated completely, no, but its output components are switched to another bus bar. Bus bars are like physical connections. You wouldn't be able to just switch the components to another bus bar. The bus bar will be switched to another bus bar. One generator bus bar. The components fed by that bus bar will lose power and become unusable. The bus bar is switched to an alternate power source so that its electrical components can be supplied with power. Yes, okay, we're back on track. This is going to be a better diagram of what I was saying. So this is... Jesus, the amount of noise that they're making now, just that I've started filming, it's ridiculous. So this kind of shows what I was talking about, but it's upside down. So you've got generator 1, generator 2. This is just like the generator breaker on-off switches, essentially. But you see this comes down to AC bus 1. And if we were to lose this, these bus tie breakers would close, BTB 1 and 2, and generator 1 would come down, and it would supply AC bus 2. Pretty simple. 17 then. During refueling, an earthing cable is fitted to an aircraft even if the tyres are electrically conductive. Why is this done? To equalise the charge between the negatively charged aircraft and the positively charged earth. To equalise charge between the aircraft and earth using a low resistance cable. To equalise charge between the aircraft and earth using a high resistance cable. To equalise charge between the positively charged aircraft and the... Well, you wouldn't be able to tell which one's positive and negative. The earth could be more positively charged than the aircraft, So it's just to equalise the charge. And you would use a low resistance cable because you want it to... you want it to be easy. Question 18 then. Consider an aircraft in which the only electrical sources are the engine and APU generators plus a battery. During the cruise, all AC generators are lost. The essential AC bus will be... So consider an aircraft where the only electrical sources are what you normally get on an aircraft. Okay, so there's no emergency generators, what it's saying. During the cruise, all AC generators are lost. The AC essential bus will be... This is quite a mean question if you're not used to... So, I'm getting ahead of myself. It's quite a mean question because this is all knowledge about buses and AC essential and DC essential. And that becomes very good and working knowledge once you are flying a big jet. But when you're not even flying these jets and you're not really sure what AC buses are and when you use them, it's quite tricky to know when the AC essential bus will be powered. Because you don't even know what an AC essential bus is. But basically, if you lose AC power, all AC generators are lost. So that means that the essential AC bus has to be powered by some DC source, aka the battery. And the battery will use something to convert the DC from the battery into AC for the essential bus, which is going to be a static inverter. So the AC essential bus will be lost as there's no AC source available to power it. No. Powered directly by the battery to provide electrical power to the aircraft. No, because it's DC versus AC. Powered from the battery via an inverter, yes. To provide electrical power to aircraft essential components, yes. Self-powered as it can store energy, no. So it's the third one. There you go, nice. Question 19, refer to the figure which logic gate is shown in figure 4. So logic gates are something I actually never talked about. I just think they're very easy to understand, and I did them in like physics when I was in, a teenager, like 15 or something, 14, and I've never forgotten them because I think they're quite easy. So now watch me get this question wrong because I said that. So what ones do I want to know? So I basically thought I'm not going to waste your time. You guys can figure out what these are. They're nice and easy to figure out. If there's a circle, it means not. If it's got a line, it means exclusive from my memory. So which logic gate is shown in figure 4? Figure 4 is an OR gate and it's a circle, so that's a NOR gate. So this nor that can go through. Yeah, there we go, perfect. Explanation. There you go, you got an AND gate, you got an OR gate, you got a NAND gate, which is the little circle, a NOT gate, which this, inverts it essentially, and a NOR gate has the little circle. Nice and easy. Question 20, the diagram. In the diagram, the component 4 is... So this is what I was talking about in the couple questions ago, that it's quite harsh for them to, put a sort of diagram like this on you, because a small aircraft that you're going to be doing all your training on won't have a complicated system like this, but this is quite a common diagram and thing that you see in jet aircraft and big, turboprops and things like that. You've got AC sources, converted DC sources, and there's also batteries that are, some components are constantly switched on by the batteries. If the batteries are powered up, you get another bus that is powered, and you got all these connections so that the electricity can flow up and down the page according to different components. You get used to it, but it was asking for component number 4, so I'll just go left to right and we'll talk through them. So component 1, you can see that we've got DC and AC. Remember that AC is the primary power source. So if we imagine a normal situation, we'd have this powered up by AC, then we'd have this DC bus powered up not from the batteries but from an AC source. So that is going to be a transformer rectifier unit, a rectifier, to convert it from whatever, like 115 volts to AC to 28 volts DC. So that's going to be a TRU, and the same on the other side, so that's going to be TRU as well. Then you've got this one here, which is going to be a TRU as well, because under normal conditions you've got, or is this going to be in emergency conditions because it's connected here? But anyway, it's going from AC sources, which are normally powered up, through to a DC essential bus. That's going to be an essential transformer rectifier unit. And then this one, it's hard to really state because there's no normal flow. I assume this diagram's in sort of normal conditions because this isn't connected, but none of them are connected. But anyway, again, quite a harsh question because I know that that's going to be a static converter because it's going from the DC essential to the AC essential. And I know that if it fails, if all these components at the bottom fail, you're going to get the batteries switching on the DC essential bus, which then goes to this component, which will then switch. This component 5 will switch, and the AC essential bus will be powered. So component 4 is an inverter of some kind. Static converter, yeah. It's just, it's not a very student-friendly question, a lot of these things. How to know current flow. AC essential bus is essential. Generator 1, Gen 2 will be fed by the emergency generator. If the emergency generator for any reason cannot supply AC power, the AC essential bus needs to be fed by the DC batteries. And it's only possible if the component... Yeah, it's quite tricky, that one. TRU, 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 as I said, an inverter and a two-way switch. So that's okay. So it can power the emergency generator, can power the AC essential bus as well. And the emergency generator can convert via the TRU to the DC essential bus. Yes, makes sense. So let's finish there. 90%, that was a good one. See all questions and answers. So I got 2 wrong in a row. So this kind of confusing one here, I need to go look at alternators and constant frequency and stuff like that. And then it was the next question we got wrong as well. So for a brushless 3-phase generator, how is the voltage output controlled? So current through the bridge circuits of diodes. I didn't even know there was. What's the explanation here? Pick 1, pick 2. Wow, that makes no sense at all to me. Yeah, so a few weak points, probably generators stuff. That was a constant frequency alternator, which is a form of generator, and 3-phase generator. So maybe look at specifically DC and AC generators a bit more, and hopefully get a bit more familiar with all those sort of things. But yeah, generally all right, 90%. And that's us for electrics. We'll move on now to looking at all the different systems on board. We're going to talk about basically the airframe design, then look at hydraulics, flight controls, landing gear, brake system, pressurization, fuel systems, fire detection. There's quite a lot to go through. And it'll probably be focused around the aircraft that I fly at the moment, the A320. because I'll have a lot more sources of information that I can pull from and examples that I can give of how these systems work. So hopefully that works for you. And we'll be moving on to that shortly. And until then, good luck and peace out.